Hey guys, this is gonna be this is my third time trying to do this one. This is gonna be the presentation on engineering failure criteria and safety factors. Basically, our ASTM standards are basically designed around us being able to pull out failure criteria and safety factors from them. So as a result, we need to know what these are before I can even ask you guys to pull them out of the text. This is fundamentally one of the most important things and lays the groundwork for the rest of our time in this team. Because of the fact that basically everything's sprouted from the idea that we're trying to prevent engineering failure. So basically, think of it this way: engineering failure is when whatever you're engineering just stops working, right? So a design factor is a factor which correlates the design factor. I have this backwards, but it basically is the minimum allowable criteria over our designed factor for whatever quantity we're trying to find. So here, like you see in this actual equation, like n is equal to allowable over design. That means that our maximum possible value gets divided by what is actually experienced by whatever we design to make sure that there is no failure, because if we go over, we are causing something to go wrong. So for example, in our static loads, stress is the big one. We have to make sure that the stress within a material which is a material property for reference. The stress in a material is always a material property. You can find it in the back of Shigley's. In contrast, we have the actual stresses experienced by the structure, which is basically the result of us doing calculations based on how the forces are interacting with the entire structure in itself. I won't go into detail about how to calculate these structural loads, but I'll have you know that it is a full process, and I am willing to explain to anyone that asks. It's just that right now, I think this is a more important thing to talk about, is just what a design factor is. Dynamic loads, usually it's just forces or accelerations felt by, in this case, because of what we're doing with our standards, we're going to be focusing on accelerations felt by the human body instead of forces felt by the system. And it's going to be compared to actual accelerations. So we're basically comparing what the human body can take versus what the ride is actually going to provide. In contrast, there are other things that dynamic loads are useful for. For example, just like making sure that, like, once we experience dynamic loads of like getting pushed forward and impulse and all that. But right now, for the most part, we're just going to be working on accelerations and like how they impact the human body. So first off, I'm going to get more into detail about static design factors. Static design factors are the easiest to explain, so I'm going to explain them for the most part in this video because I think it's really important to talk about for everyone. For static design factors, we're usually using pressure, which, as you may or may not know, is designated as force over area. So pounds per inches squared, which you may know as PSI, or newtons per meter squared, which is a Pascal. Basically, think of it like there's no physical way for us in the world to apply a force onto an object by just exerting force. Most physical ways of exerting force involves pressure and applying pressure through an area onto something. And so as a result, like everything can be simplified into a pressure, because it's fundamentally like the only natural way to apply a force. So the two most important material properties for static loads are yield strength and ultimate strength. Yield strength is the strength at which the material is no longer elastic. So you can see in this curve right here, we have basically your epsilon, which is that little e thing. That's basically just how much our material elongates compared to how much stress is being pulled on the left hand side. So you see, like right here, this is how it elongates based on how much you pull it. And yeah, there's like the correct word is strain, but strain is just the elongation of your material based on how much force or pressure you're applying to it. It can be both elongation in tension, or in compression, it will actually compress itself, and as a result, it'll be just shorter instead. So it can be negative as well. Um, ultimate strength, you can see right here, is at the very peak. It's basically when your entire thing just hits its limit and it rapidly fails. We're gonna see later on. There, I have a video that basically shows ultimate strength, and it will fail. Uh, After that, we also have fracture strength, which is where it fractures. But this doesn't really matter because once you hit ultimate strength, you'll like very quickly just fracture. There's like very little time between them. Um, Yield strength is usually super significant because if you think of stuff like gears, it's just like if you have gears meshing all the time and they like one of them yields, like what are you gonna do now? Like your gears are no longer gonna work; they're gonna deform themselves and they'll break. Like in contrast, like even though if something stops behaving the way you expect it to, because like think of it this way, we expect things to be behaving linearly. Most of our stuff we want to be in this range because if not, like we won't be able to predict what it does. And a big thing about it is while it's in before it reaches yield strength, it actually follows this linear path, but also it restores itself. So if you have tension on something and it's not as big as your yield strength and you let go, it'll return to its original form, like no matter what, because of the fact that like you have not reached a pressure where you've made something so much pressure that it physically has to change on a molecular level. Um, in contrast, if you look at ultimate strength is really bad. So like, yeah, yield strength is bad because it no longer works as predicted. Ultimate strength is bad because it'll break. Uh, so this really depends on what kind of structures we're looking at, but usually for like structures that are static and not moving, like a beam, ultimate is usually what we go for to make sure like you want to make sure like you don't hit ultimate ever. And then yield is for something that like like will have loads on it changed every once in a while. So yeah, this is like very important. And so let's look at the next video. So basically in this we have like some, I believe this is brass, and we have it in this tensile strength machine. Basically it applies pressure at the top and just like pulls on it, and you're gonna see that it basically just yanks it in tension. If you didn't know, tensile ultimate strength is smaller than compression ultimate strength. It's really hard to compress something until it breaks. But they follow similar curves, so that's why we kind of don't have two separate values. Okay, anyways, if you look at the video, you can kind of see, I'm going to move up the playback speed so it's faster. But you can see it quickly just turns into a line that's rising. I've seen this video before, but basically at about 5,000 newtons, it hits ultimate strength. And you can see that because it just starts losing it. But yeah, look, you can see right here, it did elongate from the beginning of the video. And right here, you can see it's also taking longer for it to hit, like, to increase in length because of the fact that, like, there's more resistance once you hit yield. And so you're going to see it's slowing down and the curve becomes less linear because of the fact that basically the material itself is changing and morphing as you're pulling it. So if it let go, it wouldn't restore itself anymore. It wouldn't go back to its original form. It'd just be stuck bent. Think of it like crushing a can. Like you will not restore it to its original form anymore. And right around here, we're about to hit ultimate strength. And you can see that because the curve is actually plateauing. And you can see it's kind of starting to thin out in the actual material. Like it's definitely hitting its limit around now. Once it hits ultimate strength, it starts going down again. Basically because the area is kind of starting to cut itself because it's starting to break. And it's about to break right now. You can see it. It's getting really thin. And in a few seconds, it's going to snap because, bam. Basically, you can just see how, sorry. Let me just escape that. You can just see that ultimate strength is very much like these properties aren't 100% accurate. They never will be. And we have tolerances for that. And that's why we want to make sure that when we design factors of safety, we're not trying to design for a factor of safety of 1. Because a factor of safety of 1 is not a good idea because it leaves no room for like things that you can't expect happening. So yeah, So finally, what I'm going to say is our most important equation is basically we need to know that our pressure is equal to force over area. Basically, the force that is applied divided by the area over which it is applied. This is really important because then we can use that to calculate our factors of safety. Our yield factor of safety, which is a separate material property from our ultimate tensile, there's a typo right here. This should be SUT because it could either be SU or ST based on whatever source you're getting this number from. But basically, yield will be the factor of safety for yield is your yield strength over your pressure. Your ultimate tensile strength is your ultimate tensile strength over pressure. Pressure is referred to as stress in Stiglitz. Most people refer to it as stress because you're exerting stress on the material. It's just a word for it, but like it's always in terms of pressure. So as a result, in these equations, you'll see instead of a P, you'll usually see the sigma. And a list of material strength limits can be found starting with table A-20 in Stiglitz. So basically, you know how I sent Stiglitz a couple days ago? If you have that at the very end of the appendix, there are just tables upon tables of materials, and it will tell you their ultimate tensile strength and their yield strength, which is extremely useful. For dynamics is a lot more complicated. I'm not going to get into the failure modes for dynamics because usually it's just a person dying. But a big thing about it is that I'm not going to give you guys like exact equations because that's what you guys have to pull out of those graphs in ASTM F2492 or F2291. We basically have to calculate our forces and accelerations using kinetics and Newton's second law, and that's really important because it's dynamics. And so as a result, like I can't give you these equations because I think the entire point of the document, the entire point of ASTM F2291 for sections 6 and 7 is figuring out what we need for this ride and what we have to figure out. So I need you guys to figure out, hey, what are acceptable accelerations? What should we do? How will this impact the rest of the ride system? Finally, for extraneous, you guys are a bit more complicated because most of your stuff is revolving around documentation, safety, and making sure proper procedures follow. So you'll have to deal a lot more with pass-fail criteria because you guys will basically, instead of dealing with a lot more of the theory, you'll be dealing with a lot more of the practical, a lot of the on-site practices and documentation, making sure that everything goes the way it should be going. So you guys will definitely just be looking more into documentation, what is needed, instead of trying to figure out like some like crazy math stuff. So yeah, anyways, that's all I got for today. Contact me for any questions that you guys have. This Sunday, you guys will be working together on your presentations. But if you guys don't know where to start, please message me. You guys can reach out to each other now, or if you haven't. But if you haven't done that by Sunday, like it's fine. And I hope if anything comes up, please just message me. Like I will try to help as much as I can. And yeah, anyways, thanks for listening, and I hope to see you all Sunday.